In the last class, we studied about the various kinds of broadenings that are possible in gaseous medium. We studied about the natural broadening, which is a kind of homogeneous broadening. What is homogeneous broadening? What is inhomogeneous broadening? Some examples of each kind. And we moved on to study the spectral features of a CO2 laser, and we started with a CWCO2 laser, which operates at low pressure. We saw that the operating pressure, if it is about 10 torr, and for the typical gas mixture of a CO2, we take 5 megahertz per torr as the pressure broadening, and Doppler broadening and pressure broadening in case of a CWCO2 laser are comparable. And therefore, the total broadening is a convolution of the two features, the Lorentzian and the Doppler features, and could be around 100 megahertz for this 10 torr operation. Now, when the laser operates at low pressure in a CW discharge, we also saw that the transition on which the gain reaches highest, which normally is the population inversion is maximum for 10p 20 or 10p 18 transitions, because we know that the rotational population is stored in this manner. It has a maximal behavior, and for that particular temperature, J is equal to 19 or J is equal to 17, it has the highest population, so population inversion is maximum. And once the gain on this transition, whichever transition reaches the loss line first, lasing begins there, and once lasing is set, then the rotational relaxation, that is through collisions, the same kind of population distribution curve is the population tries to come back to this kind of behavior, and therefore the rotational relaxation takes over. Although it is a little slow because the pressure is less, it nevertheless happens. The pumping is also slow. When lasing begins, the population inversion, the gain reduces. Therefore, the stimulated emission rate, which is proportional to the population inversion, that also reduces. And therefore, this dynamics, there is a kind of initial transients before which the lasing settles on a particular line, which could be, as we thought, 10p20 or 10p80. Now, sometimes because of the cavity length fluctuation, there can also be a jumping between these high gain lines. Sometimes it is 10p20, sometimes it is 10p80. Now, you see, we have said that, okay, the total broadening is about 100 megahertz. So then, will the lasing take place on all the frequencies which are under this gain curve? It is not so, because you must have learned in your previous classes that only those wavelengths for which integral number of half wavelengths exactly fit into this resonator cavity, these are called the longitudinal modes. Only those modes for which this equation, integral number of half wavelengths, exactly fit into this cavity length L, only those wavelengths can get feedback in this resonator cavity and will eventually lase. So it's not that all the frequencies which are under this gain curve, all of them will get to this. It is only those where you have cavity modes. These are the axial cavity modes. Now, suppose our loss line is such that it is somewhere here, right? You can see the loss line here. So our threshold condition, what does it say? The gain has to reach the loss line, and it has just to cross, the gain should just cross the loss line for lasing to set in. So now you see which are the modes whose gain is above loss line. Well, roughly you can say there are three modes which have gain above the loss. So these are the three modes that can get to lase in this kind of a system, and therefore your emission may be somewhat like this, right? You have three cavity modes, and maybe all of them tend to lase. So you have multi-axial longitudinal cavities which are lasing, and therefore you have multi-mode lasing. This is called multi-mode lasing. Now, I have said that these are the three frequencies, right? I have said three frequencies. Then why is it that I'm again showing a broadening here? That is called cavity line width broadening. You see, when you have photons inside a gain medium, they cannot be there forever. There is a time associated with it because the cavity photons are lost because of transmission through one of the window or scattering or some other process, and therefore there is a definite life of the photons inside the cavity. And because of this delta t, there is also an associated delta nu. This is called the cavity line width. So each cavity mode frequency is once again broadened by its own width, which is called the cavity line width. So you can see that yes, 100 megahertz full width half maximum is quite narrow, but even within that, the lasing will depend on the number of cavity modes which are actually seen above the loss line. And this multi-axial mode lasing is also aided by the fact that there is the broadening that we see here is a little inhomogeneously broad. So you have probably 3 modes lasing. Now, on the other hand, suppose our loss line is such that there is only one cavity mode which falls under the gain curve. As you can see here, if it is just one mode which falls under the gain curve, then in that case, you will have a single mode lasing. And in this single mode lasing also, you have this cavity line width, which is shown here. And further, this width, whatever it is quite less as compared to the general broadening. This will be further reduced because of the stimulated emission process. So if you see, yeah. So this was what we saw was about the CWCO2 laser. Now, if we try to come to what happens to a TSCO2 laser, where the broadening, where the pressure of operation is about 1 atmosphere. So in that case, the broadening, if we take it is 5 megahertz per torr, it becomes very, very large. The pressure broadening is it is about 4 gigahertz, while the Doppler broadening, which is proportional to under root T by N, that remains nearly the same. So a TCO2 laser can be considered to be purely homogeneously broadened because the inhomogeneity is too small. So once again, when we create population inversion, we find that J is equal to 19 is more populated, and therefore this the gain is higher in that J is equal to 19 to 20. Now, in case of high pressure operation, there is an additional gain on this 10p20 line because of a coincidence with a hot band transition. Well, this is another transition, 10R53, whose wavelength is just the same as very close to this 19 to 20 transition, and therefore that gain also gets added to this. Therefore, this 10p20 line has an additional about 6% gain than the neighboring high gain lines, and therefore at atmospheric pressure operation in a TaCO2 laser, you definitely have lasing on P20. As the gain crosses the loss line, the stimulated emission sets in through noise, from spontaneous noise, and as soon as the gain starts getting utilized in J equal to 9, you see I have shown the rotational hole burning, but this rotational hole burning is quickly filled by the thermalization process, and therefore the population once again gets back to its original shape, and the lasing on 10p20 continues. Now, here we have said that the broadening is about 4 gigahertz. If you have a cavity length of say same as 1 meter, then you have 150 megahertz as the separation between the cavity modes, and therefore large number of cavity modes can come under this 4 gigahertz gain bandwidth. So then suppose our loss line is such as we thought before. If it is like this, then this large number of cavity modes can actually satisfy the gain condition. But then our output is not really so non-monochromatic. Actually, we know that this is homogeneously broadened. That means all the molecules can contribute with equal probability to any lasing line. So the initiation, the first time when the lasing initiates on a particular cavity mode, that is also a statistical process, and therefore some cavity mode or a couple of cavity modes or 3-4 cavity modes will cross the loss line first, and lasing will begin on them. Once lasing begins on any of these cavity modes, rest of the population, which is inverted population, which is under this gain curve, it will be depleted and it will go into those lasing modes. And therefore, normally we would not say that you will have, say, 100 cavity modes lasing in a TSU2 laser, but it would be a couple of modes, several modes, 3-4 modes at most, which continue to lase. And there is a competition between them. And in general, you will say it is not single longitudinal mode, but there would be multi-longitudinal mode, and those nearby modes which start lasing first will continue to lase here as well. So if you see the pulse, this is a typical single longitudinal mode emission pulse, which we also saw before. Here you see the gain switch spike followed by the tail. And you see that we know that this tail is a result of nitrogen which is added in this. So this is from an actual laser system, but this is a multi-longitudinal mode emission. How do you know that? You can see that this emission, you can see here, this, as you see here, this is not as clean as this one. What you see is there is a lot of noise. You would not, while it looks like noise, but it actually is not noise. What it is when, suppose we say that there are two cavity modes which are lasing. Suppose they are adjacent longitudinal modes. So if nth mode is lasing, what is its frequency? Nc by 2L. And if the next one is lasing, that is n plus 1th mode is lasing, then it will be n plus 1c by 2L. Now, when these two frequencies are lasing inside the cavity, there is a beating between them, right? When there is a beating, what is the beat frequency? It can be the nu1 plus nu2, that is this frequency plus this frequency, or the difference between the two. Now, these are optical frequencies. So when you add the two, what is the frequency? I think you'll be able to calculate it, right? See, we know that our wavelength is 10 micron. So C equal to nu lambda. So nu is what? 3 into 10 to the power of 8 upon 10 into 10 to the power of minus 6. So this comes to 10 to the power of 14 hertz, which is too big to be recorded, captured by the oscilloscope. But the difference frequency, what is the difference frequency? The difference frequency is the cavity free spectral range, right? See, n plus 1 minus n is C by 2L. That is the cavity free spectral range. And when we see in the time domain, this is the beat period is (2L by C, which is the cavity round trip time. So when you actually expand this and you see, you will see that these oscillations bear a beat period, which is, if they are adjacent longitudinal modes, you will see that the beat period is 2L by C. But suppose it is not adjacent, it is n and then n plus 2. Okay, if it is n plus 2, then what will be the beat period? So the beat frequency is going to be C by L. Sorry, beat period is going to be then C by L, and the beat period is going to be L by C. So here you will see that the beat period has changed. It becomes L by C. That is, initially it is 2L by C. Now it becomes L by C. That is, it beats at half the round trip time. So by analyzing the beat period of the emission, you will know whether it is single mode, or it is 2 modes, or it is 3 modes. So you will be able to understand from the recording of the temporal profile of the emission of a laser, you will know whether it is single mode, multi-mode, or how many modes are lasing. Now, so far we have understood that the laser, whether under normal conditions, it operates either in 10p20 or 10p18 when it is low pressure, and definitely 10p20 when it is in the high pressure. But we are always saying that our CO2 laser is discretely tunable from 9 micron to 11 micron. So where is that tunability, and how do we get it? Now, you see, when the gas mixture is pumped inside the discharge, we are creating population all through, right? there is population inversion, there is a vibrational population inversion. We are populating the upper vibrational levels in 001. But then the problem is that because of the rotational relaxation in the high pressure as well as in the low pressure, the one which starts lasing continues to lase. So how do we stop the high gain line from lasing, and how do we bring about lasing of some other lines which otherwise would not lase by themselves? That is because the high gain lines are lasing at the expense of the other lines. But we want that, no, we do not want 10p20, but we want 10p22. So what do we do about it? Now, you must have heard of a prism. What does a prism do? It disperses light. That means if light falls on it, if multi-colored light falls on it, it separates them, right? So now suppose you put a prism inside this cavity. This is our regular cavity. And suppose you put a prism, right? Now, see, we have inversion over many lines. Now, suppose this is 10p, say 22, and this is 10p 20, or any other line. It could be anything. Now, we have positioned our mirror, this end mirror, in such a way that 10p20, when it comes, this is not giving it a feedback. You see, the 10p20 is getting reflected off. It is not being sent back into the cavity at all. Whereas 10p22 will get a feedback. So in this case, what is happening? There is no cavity at all formed for 10p20. So 10p20, although it is a high gain, population inversion is there, but as when you see in the cavity, it is not getting a feedback. Its threshold condition will not be met. What is threshold condition? We have that R1, R2, e raised to 2 GL equal to 1. So we see one reflecting mirror. This doesn't exist for 10p20. So in that case, what happens is that your 10p20 doesn't get feedback, whereas 10p22 is being given a feedback. You have a cavity for 10p22. So with this population inversion, when pumping is further continued and population inversion reaches the threshold, although there is 19, the population in 19 may be higher, but because it is not allowed to lase, the other line, that is 10p22, that means it comes from j equal to 21 to 22, right? This is 10p22. So when the gain on this reaches the threshold, this will start lasing, and then whatever the rotational relaxation was happening earlier, thermalization was happening earlier, that will happen for this line as well, and this line will now get to lase, and what you will have is that low gain line. So we have done it now here for 10p22, but you can do it for any other line as well. But normally a prism is not used because the dispersive power of the prism is not very great, and here the lines are very closely spaced, and therefore one normally doesn't use a prism in these kind of experiments, especially for CO2 laser. What normally is made use of is a grating. We all know about the multiple slit diffraction grating. So what it has a number of slits in a line. The size of the slit is comparable to that of the wavelength. And so when that light falls on these multiple slits, what happens is that it undergoes diffraction. You have the 0th order, that is where all wavelengths, they combine together. There is no separation of the wavelengths because it is a bright fringe, that delta lambda condition for bright fringe is satisfied for the central region. Path difference is 0 for all the beams, and therefore you have a bright fringe here. Whereas for different wavelengths, the next first order, second order, third order bright fringe locations are going to change depending on the wavelength, right? So there is a separation of wavelengths when it passes through such a slit arrangement. So this is called a transmission grating. You must have read about it somewhere or the other. So while the central peak doesn't separate the wavelengths, but the first order, when you see there is a separation between the wavelengths, and therefore this separation of the grating can be made use of. The same thing can also be obtained in a reflection grating, where we take a substrate on which grooves are created. As you can see here, the grooves are created, and it is coated normally by aluminum or gold or silver. And this gives rise to reflective grating. So you have the incident wavelength, lambda 1 and lambda 2, suppose. So this is the angle of incidence. This is the normal reflection, that is the 0th order. In the 0th order, there is no separation of the wavelengths. Both lambda 1 and lambda 2 come here. And this is the first order for lambda 1 and lambda 2. This is the second order for lambda 1 and lambda 2. So you can see that lambda 1 and lambda 2 are separated. And this is the grating equation. So d sine alpha plus sine beta, where alpha is the angle of incidence and beta is the angle of diffraction. When it is equal to an integral multiple of lambda, then you have that bright fringe, and therefore it is a function of lambda. Larger the lambda, further away will be the diffraction pattern. So this way we can actually separate the wavelengths. Now, if this grating is, suppose we put it in our cavity, right? So if this is our cavity, this is our basing medium. Okay, this is our output coupler, and from here, depending on the wavelength lambda, so you have lambda 1, lambda 2, they are separated, and we will provide feedback to only one of them. So you have your output coupler here. So you align your output coupler in such a way that lambda 1 gets feedback, whereas lambda 2 doesn't get a feedback. Then in that case, whatever be this lambda 1, it may have lower gain than lambda 2. So this will get to lace. Now, but really, will it get to lace? There is a catch here. Now, lambda 1 is here, but this is only the first order. You will also have the second order. You will have the third order. So basically, and of course also the 0th order, where lot of energy is lost. So this grating, which should ideally had been 100% reflecting, because this is our partially transmitting mirror. So this should have been 100% reflecting, but because it puts out in first order, second order, third order, etc., and the 0th order, lot of energy is lost, and therefore this, as it is, cannot be used inside as an intracavity element. So then what do we do? If the grating cannot be used as an intracavity element, what can we do? Well, the remedy to that is a blazed grating. What is a blazed grating? It is a very special type of grating which is optimized so as to achieve maximum efficiency, or the highest efficiency in the first or in one of the orders. Normally we use in the first order. It can be blazed for second order, or it can be blazed for third order. Normally it is the first order when we use in experiments, and it also sees to it that the 0th order is minimized. So this way the grating efficiency is highly improved. And how it is done? It is done by manipulating the grating element width, that is separation between two grooves. It is also modified by the height of the groove. These are so chosen that this grating acts as a blazed grating for a particular wavelength, so that there you get the highest efficiency in one order, chosen order, which may be first order or second order. So when such a system is used, then we know that, you see, this is your input. So you have so many wavelengths which are going here and there, but you are providing feedback only to the one that you want, and then you can have a cavity forming for this, and you have the output. So by making use of a grating tuned cavity, lasing on various rotational vibrational lines, starting from very low value, from very low gain line to very high gain line can be made. So you can go from 9R, 9P, 10R and 10P in this manner. Now this grating can also be used in non-litro. This is called non-litro mode. We can also go in litro mode. So what is litro mode? Litro mode is that you rotate the grating in such a way that angle of incidence and angle of refraction becomes same. So this is the angle of incidence and angle of refraction. So the use of this is that you don't require this other mirror, that is one thing. And by rotating this itself, you can change the angle of incidence. And when you change the angle of incidence, the various wavelengths which are getting feedback will also change, and therefore you can tune the wavelengths from all 9R, 9P, 10R, and 10P branches. Now, see, for CW laser, you have 100 megahertz. This is what we have written. I have just shown two rotational levels. One is 10P20, one is 10P22, and these are separated by almost 40 gigahertz. So here you can have no lasing. So you cannot have continuous tunability. Okay, and we have so many branches. These are discretely tunable, we have seen, but how to get a continuous tunability over the entire region? So suppose we go to the high pressure, that is atmospheric pressure. In atmospheric pressure, we saw that it is 4 gigahertz, but then the separation still remains 40 gigahertz. So this is the dark region. How do you go even beyond? You cannot get continuous tunability, right? So these regions are unreachable. You cannot have lasing here unless you create great gain. So now, but we know the trick that as we are increasing the pressure, we are increasing the broadening, right? If we are increasing the broadening, suppose we go to 10 atmosphere. So at 10 atmosphere, the broadening on individual line can be as large as 40 gigahertz. So large that the broadening of one coincides with the broadening of the other. So now you can see the 10P22 has merged with 10P20, and therefore now if you have a grating tuned cavity where you are slowly tuning the grating, then you can allow the lasing here or here or here, anywhere, by simply tuning the grating, and therefore you can cover the region, the dark region between the rotational levels also. So in this manner, one can go from 9R to 9P. Here, because this gap is too large, there could be some dark region, but you can again go from 10R to 10P branch, and therefore you can get a continuous tunability from multi-atmosphere CO2 laser, which could be 10 or even a little more atmospheric pressure. So what we have learned in these classes is the spectroscopy of molecules. You have learned that it has vibrational, rotational features also, along with electronic energy levels, and the transition between these rotational vibrational levels gives rise to the emission in a CO2 laser in the mid-infrared region. We also learned about the CW operation, repetitive operation, the pulsar circuits that are made use of, and also the broadening and the emission features from a CO2 laser, saying that we can discretely tune over these rotational vibrational levels, and by making special arrangements, you can actually continuously tune over the entire region. So this molecular spectroscopy that you have learned will also prove useful when you go for other molecular lasers like chemical lasers, or when you study gas dynamic laser, etc.